Let's take a look at another. This time we have vectors in three-dimensional space. We want to determine if this set of vectors are linearly independent. So same idea. If they're linearly independent, then this linear combination equation set equal to 0, the 0 vector, I should say, has only the trivial solution where C1 and C2 and C3 are all zeros. If that's the case, if it has only the trivial solutions, they're linearly independent. Okay, so we need to check how many solutions this has. Now again, I can write this as a system of linear equations. If I look at the first row, 4C1 plus 3C2 minus 3C3 equals 0. Second row, negative 3C1 plus 1C2 minus 4C3 equals 0. And last row, negative 4C1 plus, minus C2 minus 2C3 equals 0. Okay, so to solve this, I'm going to get the matrix. The coefficient matrix is 4, 3, negative 3, negative 3, 1, negative 4, negative 4, negative 1, negative 2. And the augmented part on the other side of the equal sign is 0, 0, 0. Okay? Now, if you've done this a couple times, you'll realize that you can skip this intermediate step of writing out the system of equations. This system and this linear combination equation, they're saying the exact same thing. In fact, it might even be a little easier to read this one, because notice the first vector in your linear combination equation is the first column in your matrix. The second vector is the second column. The third vector is the third column, and on the other side of the equal sign, that's the augmented part. Okay? So once you realize that, you can skip writing out this whole system of equations. Okay? But now that we have our matrix, let's get it in reduced row echelon form. Again, I'm going to use the computer, so I won't have to think too hard. First row is 4, 3, negative 3, 0. Second row is negative 3, 1, negative 4, 0. And last row is negative 4, negative 1, negative 2, 0. Let's get A in reduced row echelon form. Print it so it's nice and pretty. And so my system, once in reduced row echelon form, I get 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0. Oh, wait, I'm sorry. No, that's right. That's right. Okay. Every column has a leading entry, and so I don't have any free variables. I also know that I have a solution. I don't have any rows that look like this with a non-zero entry on the other side of the augmented bar here. Okay. So I know I have a solution, and because I don't have any free variables, it must be a unique solution. Indeed, I could say the first variable, so if we kind of compare the variables, first column is for C1, second column is for C2, third column is for C3, right? So C1, C2, C3. I could see that 1C1 must be 0. 1C2 must be 0. 1C3 must be 0. That means the only solution is the trivial solution. I need all three of those coefficients to be 0. Since the only solution to the system is the trivial solution. The vectors are linearly independent. Okay, what that means is that I can't take one of these vectors out and still expect to keep the same, to span the same space. If I take a vector out, I would lose something meaningful. I wouldn't be able to get all the places I could get to now. Okay, if I take this out, now the span of what these three vectors is not the span of just these two vectors. They are linearly independent. They're independent from one another. They're all telling me something different. And so I need them all to be able to span the full space. I don't have any redundancy.